History. Okay, yeah. Let me get my composure again.
Composure, breathing.
So yeah, this time I am actually recording, and this talk is a little bit different because of this word right here. I am talking not specifically in depth about FIbrations themselves, but more about the history behind them. And I'm going to go right from the start, so right from the notion of homotopy all the way until um, through via FIbrations, so from the point of view of FIbrations, up until the more abstract homotopy theory of model categories. And hopefully it's nice and good. So, firstly, I'll talk about the beginnings, so about the 1910s to the 1930s, if we want a time period. Then I talk about FIbrations and their development, so this is from the 1940s to 50s. And then at the end, I give a little overview of the developments of Quillin in the 1960s. So that's a little kind of timeline for you, if you like. So yeah. So of course, my goal is not actually to give a detailed account of FIbrations, but more in order to give a talk about the history behind FIbrations, so that then when you see kind of the more modern concepts in a paper or something, you kind of have a deeper understanding of where they actually came from, or at least that's my hope. So, yes, Brouwer. This is where we start. We start in 1912. Before this, the historical context is Poincaré, in 1912, sorry, not in 1912, in like the 1890s or the early 1900s, he founded algebraic topology with a series of works, analysis situs, analysis situs, but he didn't ever talk about homotopy. He talked about homology and its applications and all of that stuff, but he never talked about homotopy. Up until 1912, before Brouwer came onto the scene, homotopy was simply just a background detail, and it was never explicitly defined. But in 1912, Brouwer used the notion of homotopy in a paper, and he defined it explicitly in words, and this is the exact quote, I believe, and this is the exact quote. He defined it in words, and he defined it in a footnote, but he was the first one to use and explicitly define homotopy, which, for reference, later in the talk, is precisely defined as the following. So it's a homotopy between two maps, and they go from between two spaces x and y, and f is said to be homotopic to G, which is written as f homotopic to G like this, if there exists a continuous map H, which basically it's parameterized by the unit interval, and how it's defined is at the start, h of x0 gives you your original function f, and at the end, h of x1 gives us the other function g. And you can easily check this is an equivalence relation and all of that stuff. So this is the more precise modern definition, but the first definition was this wordy footnote by Brouwer. But we might ask ourselves, why did he care, right? Seems like something that you would want maybe, but why would he care enough to actually define it? Well, he was using a paper where he was studying, I don't know what he was studying, but one of the tools he was using was the degree of a map. And one of the key features which he was using was that if two maps are homotopic, they have the same degree. And he used this to prove one of his famous theorems, Brouwer's fixed point theorem. And what it says is that every continuous function between the n disk and itself has a fixed point. And the key thing to note is that homotopy was a key ingredient and not just a background detail. So this is obviously a shift from before, where it might have been a background detail in maybe even some integration or something, or some complex analysis. It might have just been like a small little detail in the background. But now it's actually being used for the first time properly as a key ingredient in the proof, where it actually needs to be explicitly defined in all of that stuff. And Brouwer actually conjectured that the converse of this statement was true, i.e. that the degree implies the degrees being the same implies the maps are homotopic. But actually, nobody really cared enough to try and solve it until Hopf solved it in 1925. And indeed, Hopf is the next person in our story. So, yeah, homotopy did just remain a footnote, to be fair. So, Brouwer, although he was the first to define it, didn't really ignite the study. Whereas Hopf did that because he used this notion of homotopy in order to study maps between spheres. Now, the interesting thing about this is, because spheres have only two non-trivial homology groups, H0 and Hn, or in this case Hm, this map here, these induced maps with homology, will actually be pretty useless. They'll contain little to no information. However, Hopf discovered that actually, if we look at homotopy classes of maps between spheres, we get rich amounts of information. And of course, the famous discovery of his was the Hopf fibration. And this was in 1930. And the Hopf fibration was the first ever map to be discovered between two spheres of different dimensions. It was the first ever map to be discovered that was not null homotopic. That is, it's not homotopic to the trivial map, like the constant map. And of course, and indeed, not only this, he showed that there were infinitely many distinct homotopy classes of maps. So there's rich amounts of information here. And compared to homology, which has been pretty useless in this because it's pretty trivial on spheres, Hopf was the first one to show that homotopy gives us information that homology can't sometimes. And actually later in 1935, so he continued work on this, and in 1935 he actually generalized his results to more general spheres from 2n-1 to Sm. So he was really he really ignited the study. And now that people were seeing, okay, this is actually giving us information, people started to study it. And the next person in our story is going to be Hurwitz, but firstly we have to look at the definition of the fundamental group. Now, a loop in a space X is a continuous map between the circle and the space X. And it's given two loops, we define the concatenation of two paths F and G as traversing F and then traversing G. And the important thing is we go by F at 2 times speed, and we go around G at 2 times speed. So we go around in one loop, which gives us closure. Now, what else do we have? Because we want this to be an algebraic structure that we can study, so we want it to be a group. So we have closure, we have the identity, because if you do the constant loop, that is, you just stay in the same place, and then you do G, you traverse G, well, obviously, you're just going to get the same thing as just going around G. So we have the identity. Great. Now we have inverses, because if we go F, and then we go the other way round, that's the same as just doing nothing. So that's the inverse. And the more precise notion of the other way round is F of 1 minus S. However, we don't have associativity, because if you do F star G star H, what you're doing is you're going around F at 4 times speed, you're going around G at 4 times speed, and you're going around H at 2 times speed. However, if you do F star G star H, you're going around F at 2 times speed, G at 4 times speed, and H at 4 times speed. And so these are not exactly the same. So we don't have associativity kind of like on the nose, I guess you could say. However, don't panic, because associativity holds up to homotopy. So if we do F star G first, so we go around F and G 4 times speed, and then we go around H. No, I did not mean to write that. I meant to do that. This is homotopic to doing F and then star G star H. So going around f at 2 times speed and then g4 and h4 times speed. And you can, if you really want, you can look it up how to explicitly define this, but that's basically what happens. And so therefore, we have a group because we've solved associativity as long as we just consider things up to homotopy. And so we can define the fundamental group as, well, homotopy classes of maps between the circle and the space X. So just keep this in mind. An amusing note, actually, is upon seeing this definition, S1X, one would want to study between the n-sphere and X as well, and check first kind of put a little footnote about this in 1932. But in 1932, because they were abelian for n greater than or equal to 2, the pi 2 is pi n is abelian for n greater than or equal to 2. Čech basically thought this is not going to give us information that homotopy, that homology can't, so he kind of discarded it. He just didn't study it. It was a curious footnote. And so, yeah, and the reason for this, I think the reason for this kind of reasoning was because the first homology group is precisely the abelianization of the fundamental group. And so Čech kind of thought, well, if pi 2 is abelian, then it's not going to give us anything different to H2. Which is very amusing in hindsight, of course. And it was indeed Hurwitz who was the first one to properly study these homotopy groups. So how did he stumble upon these groups? Because he actually didn't do it in the same way as you might think. Hurwitz was all about studying maps between, topology of maps between spaces. And he was interested in the topology of such spaces. And in particular, he was interested in the loop space, which is the set of all maps between the circle and X. Now, if we define a path as a map between the unit interval and the loop space of X, and a path in the loop space is this, then with the correct, okay, let's look at what this actually is. This is a map I from the unit interval to a map between S1 and X. Now, this is, okay, let's say 0. What's 0 getting mapped to? 0 is getting mapped to some f of x, let's say. Therefore, this is the same under the correct topology, which Hurwitz sorted out the details of. This is the same as a map between S1 cross I and X, which now just sends x 0. This just sends it to f of x, as we defined above. So it's pretty much equivalent. We're just packaging this information into one map. But now let's look at this. This one map that we've packaged everything into is precisely a homotopy between loops at x0. And therefore, the path components, because these are the sets of all paths, remember, the path components of the loop space is precisely the fundamental group. So in modern notation, that would be this. Pi 0, which is the path components, of the loop space is precisely pi 1 of the original space. And so, using this, Hurwitz generalized inductively. So he defined the nth loop space of X to be the loop space of the n-1th. So he did this kind of inductively. And of course, he figured out all the base points. That's not too major if you want to figure that out. It's he managed to figure out the base point shenanigans. And okay, so this is how he defined the nth loop space. And so what he did was perfectly logical. He defined the nth homotopy group of the X at x0 to be, well, I don't know why I'm writing it out again. He defined it to be the fundamental group of the n-1th loop space of X. And of course, with modern homotopy theory, we know this is true. So he gave the exact same definition as in modern homotopy theory, or an equivalent one, I should say. And so in a series of 4 papers between 34 and 36, so in the mid-30s, Hurwitz really injected life into homotopy theory. He kind of really kicked off the study of these homotopy groups, which of course we know are very crucial and still get studied today. For example, some of the theorems and stuff that he did, he refined Hopf's results. So remember, Hopf showed that there were infinitely many homotopy classes of maps between the 3-sphere and the 2-sphere. Hurwitz restated this with pi3 of S2 being isomorphic to the integers. One theorem that was really, really important, one theorem, okay, not that important for FIbrations, but one theorem that was important was that there's an isomorphism between the first non-trivial homotopy group of X and the corresponding homology group. This is an isomorphism. And this is known as the Hurwitz theorem. Which is just a really deep thing, and because homology groups were so interesting back then, a connection like this would have been really important as well. So Hurwitz really studied things like this. He was refining results. He was, he put out a series of 4 papers, and in the mid-1930s, people really knew what you're talking about when you're saying the nth homotopy group. One other thing that Hurwitz did actually was, up until now, F was homotopically equivalent to G. So what we're doing, we're classifying maps. But now, what he's done is he's defined a space X as being homotopically equivalent to a space Y. So now we're classifying spaces. How does he do that? Precisely, it's this. So if there exist maps between X and Y and X, such that their compositions are homotopic to the identities. And so this is how he's managed to classify spaces. Of course, note that this is just a weaker version of homeomorphism. And before I move on to FIbrations, I actually have to say a shout out to Freudenthal, who in 1937. So right now we're 1930s, so we're really around this time. Well, in 1937, Freudenthal kickstarted stable homotopy theory. And he introduced the suspension theorem, Freudenthal's suspension theorem, which was particularly important. However, because we are studying FIbrations, this is not going to be important for us. So I just wanted to mention that, but not going to elaborate on that, at least in this talk. So I would ask if there's any questions, but I've already recorded this with the same audience, so I'm just going to recap before I move on to FIbrations. 1912, we have Brouwer. What does he do? He defines homotopy. We have 30. Hopf defines his fibration. His map, I'll call it for now, the Hopf fibration, which shows that homotopy can be more useful than homology in certain contexts. And then from 1934 to 36, Hurwitz defines pi n and classifies spaces. Like so. Okay, that's the recap. Now, we have to move on to FIbrations. This is a bit more of a technical slide, but you'll see why it's important in a second. So in the early 1940s, so this is while World War II is going on, mathematicians from across the world had identified a very specific property, which is known as the homotopy lifting property, which was very useful. What is it? Okay, so let's say we have a class of topological spaces C, and X is a member of this class. Then, a continuous map P from E to B is said to satisfy the homotopy lifting property if, for some map between X and E, and for some homotopy H from X cross I to B, and of course this map here down here is just the inclusion. If there exists a lift, a homotopy H tilde, which makes everybody commute, so it makes all the triangles commute, then we say that P satisfies the homotopy lifting property with respect to C. So for example, if C were cell complexes, then we'd have P satisfies the homotopy lifting property with respect to cell complexes. So, okay, that's what it is. Now, this seems very random right now, I'm sure, but this is why it's important. The reason why it's important is that if we have a map P that satisfies the homotopy lifting property, and if we define the fiber of this map to be the preimage of the base point of B under P as the fiber, and we call that F, it actually, all of this information actually fits into a long exact sequence of homotopy groups, as you can see in the sequence here. And so long exact sequences are really helpful. From a purely algebraic standpoint, we can extract information from this. For example, if we have some, say, for example, some section or something like that, like this or something, just as an example, we would have that the sequence splits, and of course if the sequence splits, then we can express the nth homotopy group of E as being isomorphic to a direct sum of these two homotopy groups. For example, one example of this is using the hop fibration. One can show, simply by using a long exact sequence, that pi n of S3 is isomorphic to pi n of S2, where n is greater than or equal to 3. And this is just one example, of why long exact sequences are helpful. And so, okay, mathematicians have discovered this, and they've got this property that gives them this sequence. So what do? They try and form a set of conditions. They try and form a set of conditions. So they want conditions that imply, also I've done this, they want conditions that imply the homotopy lifting property. And sure enough, they found them. Remember, this is the 1940s though, so this is World War II. And so we have 3 groups of mathematicians all working at the same time, all trying to find the same thing, but they can't talk to each other because it's World War II. So what do we have? We have in 1940, we have Hurwitz and Steenrod working together. And they found a manageable set of conditions on the map P to satisfy the homotopy lifting property. Then, unknowingly to these two, Ehresmann and Feldbau were pretty much defining fiber bundles as we know them today, and they were proving the homotopy lifting property on them. And in Zurich, at the same time, Ekman defined what he called retractable partitions, and these were a stronger version of the definition that Hurwitz and Steenrod gave. But all of these had one thing in common. they were searching for conditions, and they were then using them to get the homotopy lifting property as a consequence. And they defined the map P as being a fibration using these conditions. But in terms of fibrations, a key turning point came in Serre's thesis, which was quite groundbreaking really in homotopy theory in general. But he also defined fibrations in a different way as well. So we're going to look at his work briefly. So, before we had conditions implies homotopy lifting property. Now what do we have? Serre defined a fibration as a map that satisfies the homotopy lifting property. So now the homotopy lifting property equals the conditions. The condition is that you satisfy the homotopy lifting property with respect to finite complexes, so with respect to quite a large class of spaces. Now, of course, this is for us talking, because a question I had in the last talk was, well, what was because this is just a definitional change. So what was the technical kind of, why was his thesis so groundbreaking, kind of technically speaking? I think that was more to do with his use of spectral sequences in order to prove results about homotopy groups of spheres. For example, he managed to prove that pi 4n minus 1 of S2n is always infinite, is the integers plus finite stuff group. For example, he proved this result, for example. But for us, the crux of the changes that he made were fibrations. He completely changed the way we thought about fibrations, because instead of defining a set of conditions that satisfy the homotopy lifting property, he made the homotopy lifting property the conditions. And that was a big shift that we still use today. Now, he defined it as with respect to these complexes. Hurwitz removed all restrictions in 1955, and today we still both use Serre and Hurwitz fibrations. We still use these things, so yeah. Now, another thing that he did was he introduced the path space fibration, which is a special example of a fibration. And he just did lots of good work in that thesis, basically. But the main change from our point of view is that the homotopy lifting property became the conditions. If you look at a definition in a modern textbook, the condition is that it satisfies the homotopy lifting property. And we have both notions of a Hurwitz and a Serre fibration still being used today. Okay, I think that's everything for fibrations. Yes, so I'm just going to give a brief timeline before I move on. 1940s. We have 3 groups of mathematicians working to find conditions where the homotopy lifting property holds. But then in 1951, Serre published his thesis where homotopy lifting property equals conditions. So a map is a fibration if it satisfies the homotopy lifting property. Yes? Okay. Yes, and that is, for us at least, when we're talking about fibrations, that is the main change. And then in 1955, we have Hurwitz slightly, let's say, refining the definition of Serre. Definition. So, yes, that is the situation right now, and these FIbrations, combined with spectral sequences, which you can actually watch a talk about on this channel, where I do talk about spectral sequences, including the stereospectral sequence, but the FIbrations, along with all of this other machinery, have proven themselves to be useful machinery for various reasons. Now, the last thing I want to talk about is I want to give a brief overview of the beginnings of abstract homotopy theory with Quillen and model categories. So they were introduced in the 1960s. I believe more precisely it was 1967, but I don't want to risk it, so I'll just say 1960s. Now, there's two goals that we have in abstract homotopy theory. Firstly, we want our model, let's say, to have appropriate equivalence relations. So these should, just as isomorphisms in the category of topological spaces corresponds to homeomorphisms, we want an appropriate notion of equivalence relation between maps and objects, and we want them to correspond to homotopies between maps, and we want them to correspond to homotopy equivalence between spaces. So that's the first thing we need. The second thing we need is we should actually be able to do homotopy theory. That is, we should actually be able to compute fundamental groups, or homotopy groups more generally, and, have FIbrations and all of this stuff. So we want this too, because that's part of the model. That's part of what homotopy theory is. So, and of course, we can't just define this willy-nilly. Whatever abstract sense you give to homotopy, it needs to be recoverable. You should be able to recover the standard topological meaning from the abstract version. You should be able to go from abstract to topological. It shouldn't just be some random thing that we're calling homotopy. We should be precisely able to extract the topological information. And Quillen was the first one to do this with his notion of a model category. And I'm not going to give the precise definition here, because that's quite long, and that deserves its own talk, really, about model categories. But I'm going to give you, if you want to look it up after this talk, what the definition actually is, I'm going to give you an overview of what you're actually looking at, basically. So firstly, once we have a model category C, one can define the homotopy category, which is denoted like this, in which weak equivalences are isomorphisms. So the homotopy category of C is a homotopy theory, in quotation marks, because the notion of equivalence in this category is precisely the weak equivalences which we want. And Quillen actually went further. He said, okay, I can tell you when two homotopy theories are giving us the same information, and this is known as Quillen equivalence. And an example of Quillen equivalence is that if we do the homotopy category of simplicial sets, this is Quillen equivalent to the homotopy category of topological spaces. And so that means that, roughly speaking, these are giving us the same information. That is, we can model extremely well the study of ordinary homotopy theory via simplicial sets. And of course, there's much literature on simplicial sets, on the homotopy theory of simplicial sets. And indeed, a note that I thought of is, well, infinity categories are defined in terms of simplicial sets. And of course, I don't actually know the history behind infinity categories, so I don't know how they first came about. But it doesn't surprise me that this infinity category thing, which also wants to give us these weak equivalences. It also wants to do these things, give us an appropriate notion of homotopy. It's no surprise that these are also to do with simplicial sets, because simplicial sets are an extremely good model because it's homotopy equivalent to topological spaces. And this is the kind of thing that abstract homotopy theory allows us to do. It allows us to make statements like this. And it allows us to make them precise, because you'll see if you look this up, Quillen equivalence is a complicated thing. It's got, derived functors flying about, all of this stuff. So, it's very precise machinery is being used to convey these abstract notions. And finally, I should talk about where do FIbrations come in. FIbrations come in, if you look at the definition, you'll see two main features: weak equivalences and co-FIbrations. Roughly speaking, weak equivalences and co-FIbrations and FIbrations, when I say co-FIbrations, I mean both co-FIbrations and FIbrations, cover the two goals we needed. Remember, goal number one was appropriate notion of homotopy. Notion of homotopy. Goal two was do homotopy theory. Okay, so these were the two things we wanted. Number one is solved by weak equivalences. Weak equivalences allow us to formalize the notion of homotopy in a general kind of setting, like in a category or something, or in a model category. This is what the function of the weak equivalences are. And they have all sorts of axioms that they need to satisfy. And this is further evidenced by the fact that in the homotopy category, these things become isomorphisms. But these things do not allow us to do number two. And number two is to do homotopy theory. So it's all well and good having an appropriate notion of homotopy, but we need co-FIbrations and FIbrations in order to do homotopy theory in these settings. And so together, these things work together. These things work together in order to form the definition of a model category. And poetically enough, in the definition of a model category, I believe that these co-FIbrations and FIbrations are required to satisfy the homotopy lifting property, which models the same approach that Serre had in 1951 when he defined a fibration as something that satisfies homotopy lifting property, which is, I don't know, I find that quite poetic. But so now we see how fibrations are still relevant today in the modern kind of homotopy theoretical landscape, because they're just so useful. They just give us this information. It's miraculous. And these weak equivalences obviously allow us to do number one. And yeah, that's where I finish. So we've come from 1912 to about 1960. I'll say 1969. So we've covered this period of homotopy theory from the point of view of fibrations, and of course I've given you a little insight into abstract homotopy theory. And its kind of goals and what it's studying. And obviously, if you look on arXiv and you see infinity category, triangulation, blah, 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 that's probably studying abstract homotopy theory. And it's got these goals in mind. And I've also covered the work of Serre, which is classical homotopy theory. And all of the stuff that came before that with the homotopy groups and stuff. And on arXiv, if you see like studying the Adams spectral sequence or the blah, 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 that's probably studying classical homotopy theory. And its goal is simply to compute, fundamental homotopy groups and to study the notion of homotopy kind of in the category of topological spaces. whereas this is in a more general kind of category. It could be simplicial sets or something like that. So we've got these two notions, and in both of them, FIbrations are important. And that's kind of where I wanted to finish off. I pray that I actually clicked record this time. And if there are any questions that you thought of during the talk which you didn't think of last time, then feel free to ask. But if not, then hopefully it will be ready to upload to YouTube. So yeah, I'll just wait for a second in case anyone has anything to say. All right, cool. So I am going to see whether that recorded. Yes, it was recording. Okay.